Hello and welcome to STAT 441 at Virginia Commonwealth University. In this lecture, we will learn about how to conduct a hypothesis test for the difference between two population means, and we will consider the case when the samples are independent of each other. Okay, so consider this. Let's say we have two populations with mean mu1 and mu2, and we would like to conduct a hypothesis test for the difference between the two population means. The sample sizes that we are considering for the first case, the samples are independent of each other and both samples are greater than or equal to 30, which will give us a large sample and we will be able to use the Z statistic. So here's a summary of how we can conduct the test for mu1 minus mu2, which is our parameter. If we conduct a one-tailed test, our null hypothesis is mu1 minus mu2 equal to the value that we are trying to compare the difference with, usually 0. Mu1 minus mu2 could be a greater than test, less than test, or if it's a two-tailed test, it would be a not equal test. So that depends on what we are trying to test to see. The test statistic in this case will be y1 bar minus y2 bar, which is the difference in the two sample means, minus d0, which is the value in the hypothesis. And then the denominator is sigma of y1 bar minus y2 bar, which comes from the sampling distribution of y1 bar minus y2 bar. And it can be written as square root of s1 squared divided by n1 plus s2 squared divided by n2. So we can use the rejection region just like we've used for the other tests, but we will use the p-value method here. So p-value will be, depending on the type of test, the sign could be greater than or less than. So if it's a greater than test, the p-value will be probability of z greater than z calculated, which is this value. If it's a less than test, it will be probability of z less than z calculated. And if it's a two-sided test, the p-value can be calculated as 2 times probability of z greater than absolute value of z calculated. And the way we make the decision and conclusion stays the same, just like we've used before. We will compare the p-value with alpha, the significance level. If the p-value is less than alpha, we reject the null. If the p-value is greater than alpha, we will fail to reject the null hypothesis. Okay, the assumptions here for this test will be that the two sample sizes are sufficiently large, both greater than or equal to 30, and the two samples are independent of each other. So with this information, let's look at an example. To reduce costs, a bakery has implemented a new leavening process for preparing commercial bread loaves. Loaves of bread were randomly sampled and analyzed for calorie content both before and after implementation of the new process. Okay. A summary of the results of the two samples is shown on the table in the next slide. Do these samples provide sufficient evidence to conclude that the mean number of calories per loaf has decreased since the new leavening process was implemented? And we will use a significance level of 0.05. Okay, here's the information that's given to us. So new process is first, and then we have the old process. And we're trying to see if the number of calories in the new process is less than the number of calories in the old process. So let's see how we will write our hypothesis. So let mu1 be the mean calorie content per loaf by the manufactured by the new process. Mu2 is the mean calorie content per loaf manufactured by the old process. And we are trying to see if mu2 is greater than mu1. This is the new process, this is the old process. So we can write it as mu1 minus mu2 equal 0 versus mu1 minus mu2 less than 0. Okay, so our test statistic for this test will be y1 bar minus y2 bar minus 0, because that's the value we're testing against. We just want to see if mu1 minus mu2 is less than 0. And then sigma of y1 bar minus y2 bar. The assumptions here will be that the two samples are the two bread loaf samples are independent of each other. Okay, so we plug in all the information. This is the first mean value for the new process, second y2 bar for the old process, and then we have the standard deviations for both and the sample sizes for both. So when you plug in the information, you should get your test statistic value as negative 1.41. Okay, now remember, we will use the z table to find the p-value. And since it's a less than test, we will find the probability of z less than negative 1.41. Okay, so going back to the table, so basically we will be looking for 1.41. Okay, this is the value here for 1.41, and you subtract that from 0.5. So 0.5 minus 0.4207 or 0.0793 is the p-value. If you compare this p-value with alpha, which is 0.05, the p-value is greater than alpha, which means we will fail to reject the null hypothesis, and the conclusion will be that the sample does not provide sufficient evidence to conclude that the new process yields a loaf with lower calories. Okay, so that would be our testing for the difference of two means when we have large samples. Now let's see what happens if we have small samples. So the way we write the hypothesis stays the same. We have mu1 minus mu2 greater than, less than, or not equal to for one-tail and two-tail tests, but the test statistic will be a t-statistic. And the test statistic will be y1 bar minus y2 bar minus d0 from the hypothesis. And then for the variance, we will use a pool variance, assuming that the two variances are equal. So if we first calculate a pool variance, which is kind of weighted for the sample size, so n1 minus 1 times s1 squared plus n2 minus 1 s2 squared divided by n1 plus n2 minus 2. So this will go in here, and this will be our test statistic. Okay, now for this test also we will use the p-value method. For the p-value method, since it's a t-distribution, we need probability of t greater than, less than, or for the greater than or less than test. If it's a two-sided test, we will use 2 times probability of t greater than absolute value of t calculated. The degrees of freedom will be n1 plus n2 minus 2. We will use the t-table for computing the test, or the p-value for this one. Okay. Here are the assumptions that go with this test. The first assumption is that the populations from which the samples are being picked should be approximately normal. The second assumption is that the variances of the two populations is equal, and the two samples must be independent of each other. Okay. So based on that information, again, let's look at an example for conducting a test where we are comparing gas and electric energy. An industrial plant wants to determine which of the two types of fuel, gas or electric, will produce more useful energy at the lower cost. One measure of economical energy production, called the plant investment per delivered quad, is calculated by taking the amount of money invested in the particular utility by the plant and divided by the delivered amount of energy. Okay, the smaller this ratio, the less an industrial plant pays for its delivered energy. So let's see how we will conduct the test. Independent random samples of 11 plants using electrical utilities and 16 plants using gas utilities were taken, and the plant investment per quad was calculated for each. We have the data listed on the next table. Do these data provide sufficient evidence to indicate a difference in the average investment per quad between all plants using gas and all those using electrical utilities? So we just want to see if there is a difference. That means it will be a two-sided or a not equal test. This is the information we have, the ratio for electrical and gas plants. Again, as you can see, these are small samples, so we will use the t-distribution. Okay, so here is the null and alternative hypothesis. The null hypothesis will be mu1 minus mu2 equals 0 versus mu1 minus mu2 not equal 0. So it could be less or more. We just want to see if it's not equal. Okay, So for this one, we will need a pool variance. Again, the assumption is that the variances are equal, the two populations are approximately normal, and their samples are independent of each other. From the data, we will calculate the mean and the standard deviation for both samples, and then use it to calculate the pool variance. So we plug in all the information. We have the first sample size is 11, second sample size is 16. This is the mean for each samples, and we have these are the standard deviations for both samples, and we calculate the pool variance. Okay, so thus assuming that the two distributions are approximately normal with equal variances, we can calculate our test statistic. Y1 bar minus Y2 bar, the two sample means, minus P0, which is again 0 in this case. This is SP squared, the pool variance. And then these are the two sample sizes, 11 and 16. That gives us 0.68 as our test statistic. Okay. With this, the p-value for a two-sided test, 2 times probability of t greater than 0.68 with degrees of freedom 24. So from the table at degrees of freedom 24, we can see here at degrees of freedom 24, this value is 1 point something, but 0.68 is even smaller than this. So this largest value here is 0.10. So our p-value has to be greater than 0.10. But again, it's a two-sided test, so we double that. So we can say that the p-value is greater than 0.2. Okay, so even though if we don't have the exact p-value, but we can still make our decision by comparing with this alpha value. P-value still exceeds 0.05, and therefore we have insufficient evidence to reject H0, or we fail to reject H0. So the conclusion in this case will be that we cannot conclude that the mean investment per quad levels for the plants with electric and gas utilities are different. Okay, so this is the hypothesis test for difference in means for independent samples. Thanks for watching.